Here we need to solve the equation for the interval 0 to 2 pi. This essentially just means we're going to solve this for any angle that works, but just within one full rotation. So 0 to 2 pi. That's one full rotation. And you might notice actually that 0 has the bracket mean we want to equal possibly an angle of 0. But as we go around and we get back to here, this parentheses means at 2 pi, or the full rotation, 360 degrees, we also don't want to count that because that's just like the 0 degrees. So that's what we need to do. For this equation here, it looks like it's already in factored form. And these two factors, this factor here and this factor here, we need to make it so when you multiply them, they equal 0. We can use what's called the zero product property. This first piece could be 0 multiplied to make 0. So let me try and set up an equation for that. I want to know when this first factor equals 0, or this second piece could equal 0. It could be something times 0 here to make 0. So that's the zero product property. So I just need to solve each of these situations. I think I'm actually going to solve the right one first just because it just seems simpler. I just need to know when the sine of x equals 0. Of course, I could do the sine inverse and do that on my calculator and get an answer, but let me use some other strategies. One really good strategy for this one is actually just thinking of the graph of sine. If you know the graph of the sine function, the graph of the sine function looks like this. It goes up and then down and then back to there, and of course that keeps repeating. It's cyclical, it's periodic, it just keeps repeating that. So I'm looking for when this function, which angle makes this function equal 0? Well, it actually starts at 0 here, the origin 0, 0. So that tells me one angle to solve for this is when x equals 0. 0 degrees or even 0 radians. Then of course it looks like it hits 0 again. And that's right here in the middle of one full cycle. I didn't really draw it evenly, but that's okay. It's the middle of a full cycle. And of course a full cycle is out here at 2 pi. But remember, we don't want to equal 2 pi. That's actually just like the beginning, and you can see here it repeats the cycle again. The end is just like the beginning of this, so I don't want 2 pi. That doesn't count. 2 pi would be an answer, but I'm not going to include that. But I do want this one here in the middle, and that would just be at pi. So x could equal 0, or x could equal pi. I'll just list those two there. So actually, here's two answers. These two answers make this whole thing equal 0 because they make this factor equal 0. Now, we could have some other answers here. Let's actually solve this other factor when this factor is equal to 0. This one takes a little bit of work. I'm just going to add 1 to both sides and then rewrite it. And it looks like I need to divide both sides by 2. And then now I have when the cosine of x equals a half. So now I need to solve this. I need to solve this within one full cycle or rotation. Now the sine problem I actually solved by looking at a graph. It's hard to look on a graph and see where it's up at a half. Seeing where it's at 0 is pretty easy, but seeing where it's at a half isn't so easy. I might actually, I could do the cosine inverse and find out what angle makes this work, but I'm actually going to use just the good old butterfly. So let me draw a butterfly over here, the unit circle. The cosine needs to be a positive half. That's the adjacent and hypotenuse. So if I just kind of draw a piece of the butterfly here, I need to know what angle here is going to make it be an adjacent of 1 and a hypotenuse of 2. Well, this triangle should look, pretty familiar here. This is just a 1, 2, square root 3. I could even do Pythagorean theorem and solve that, but I should really recognize that. Which means I know what angle that is. That's actually a 60-degree angle, but technically we're supposed to be in radians. So I could say it's 60-degree angle, which is actually pi over 3. So it looks like pi over 3, if I plug in cosine of pi over 3 in radians, that would give me a half. So I actually just found another answer. Another answer is pi over 3. However, this one had multiple answers. Maybe this one has multiple answers. We need to think about that. We actually want to solve this within one full rotation. And we already found one answer in quadrant 1. Is there another quadrant where the cosine is going to equal a half? And yes, there is. If you remember, all students take calculus. this quadrant here, the fourth quadrant, is another quadrant where the cosine would equal positive 1/2. In these other quadrants, it would actually equal like negative 1/2, you know, with a particular angle. So let's actually, I'm going to redraw this, but this time I'm going to do it for quadrant 4. So what would that be? Well, again, it would still be, so some mystery angle here, it would still be a 1 for the adjacent and a 2 for the hypotenuse. Of course, the opposite would actually still be square root of 3, but technically in this quadrant, this would be negative square root of 3. But we're not really worried about that because, again, we're focused on cosine, which is adjacent and hypotenuse. We're not worried about the opposite so much. But really, what angle is this? Well, I mean, it's the same triangle. It's actually a 60-degree angle, but 60 degrees would put me in quadrant 1. This would be like a negative 60-degree angle. However, we don't even want a negative 60-degree angle. We actually want to be able to get there within one full rotation going positive direction. So how do we get to here? If this is 60 degrees, what angle would get you around there? Well, that would actually be 300 degrees. That's what would get me into quadrant 4. But of course, we got to think in terms of radians because this says from 0 to 2 pi or radians. Remember, 60 degrees was actually a pi over 3. Okay, we don't want that though. We don't want pi over 3. But we're actually almost a full rotation. And a full rotation is actually 2 pi, which in terms of thirds, right, that would be actually 6 thirds or 6 pi over 3. That would be a full rotation. But we're actually pi over 3 shy, that's 60 degrees shy, from a full rotation. Just like we were 60 degrees shy from a full 360, it would just be 300 degrees, or a pi over 3 shy from 6 pi over 3. So that's actually 5 pi over 3, because we're 1/3 shy. So that would actually be our quadrant 4 angle that we want to get all the way to here and have another cosine that's a half. So the other x that would work, not only just pi over 3, but also 5 pi over 3. So now we actually have all 4 answers. There were 2 answers here from the sort of the second piece. We started with that. And then actually, there are 2 answers here, and that's actually from the first piece. So there are our 4 answers. Let's check out another problem here. This one also says solve the equation for that same kind of interval. The only difference is this one looks like it's in standard form. It kind of looks like a good old x squared plus 2x plus 1 equals 0. But it's not just x squared, it's actually sine square of x and 2 sine of x plus 1. But the idea is we actually need to get this into a big old factored form. Okay, I'll leave lots of space because it might need it. So I need to get it into a big old factored form. Then I can take this piece equal to 0 and this piece equal to 0, just like in the previous problem. So what I need to do is factor this thing. If you like, you can just use a good old area model. Some people might be able to look at it and just see how to factor it, and I'll point that out here in a second. But let's just use our good old strategy. We put the first in the first box. That's sine square of x. Put the last in the last box. That's just 1. And then, of course, we multiply that diagonal. That just makes 1 sine square of x. And that's our multiplication piece, because this diagonal also has to multiply to that. And then we have to add to make the middle piece here, the middle term of our standard form. And so that's 2 sine of x. All right, what 2 things multiply to make sine square of x and add to make 2 of the sines? Well, that's just a sine of x and a sine of x. They multiply to make sine square, and they add together to make 2 of the sines. So those are the 2 pieces that go in here. We got sine of x in one piece and a sine of x in the other piece. So our area model is filled in, but now we need to figure out what's our base and what's our height. So what is in common here? A sine is in common in the first sort of column. What's in common here? Well, nothing really, unless I put the fact that this is a 1 sine of x. In fact, so is this a 1 sine of x. So what's in common here is actually just the 1. And then same thing across here. This first row, we got sine of x in common, and then a 1 in common. And you actually see that sine of x times sine of x is sine square, and then 1 times 1 is 1, and of course 1 times sine is just the 1 sine in each corner box. So there's our factored form. The base is sine of x plus 1 from our area model, and the height is also sine of x plus 1. They're the same. It's a nice perfect square. Now we can just solve each of these pieces, this factored form, we can solve to see what makes it 0 using the zero product property. So I need to know when the sine of x plus 1 equals 0, and I also need to know when the, oh wait, sine of x plus 1 equals 0. We're going to get the same answer for either one, so we really just need to solve one of these things. So let's go ahead and solve it. Of course, we need to rewrite this a little bit by subtracting 1 from both sides. And so I just need to know when the sine of x equals -1. Now, this is actually a special one. You could, of course, just do the sine inverse on your calculator and see what it says. Watch out, though. We do need to get this in radians. Let me just do this using just kind of like the graphing method as before. I could also try the butterfly method, but here the graphing method is good, and here's why. Because this is going to be a quadrantal angle. When is the sine of x equal to -1? I could try and make it like, opposite over hypotenuse, but when is the opposite one and the hypotenuse one? When are they one and the same? That's an awkward situation. Of course, this has to be a negative thing, but let me actually just use the graph. If you know the graph, it actually helps really well for this. Here's the graph of a sine function. It goes up, down, and then of course it continues that. It keeps going. And we need to know not when it's 0 this time, but when is it -1? And it's actually right down here. That's when it gets to its lowest. It gets up to +1 and goes down to -1. That's not here at 0, it's not at pi, and it's not at 2 pi. Remember, this is 2 pi, a full cycle. This is the middle of the cycle at pi. It's actually right between that. It's like 1.5 pi, or 3 pi over 2, 3/2. So that's actually our answer. It's when x equals 3 pi over 2. That in terms of degrees, that would be what, 270 degrees. And you can actually see that kind of using the butterfly method. Now that I know the answer, using the butterfly method, well, it's hard to draw a triangle where the opposite is something like 1 and the hypotenuse is 1 when they're one and the same, right? If I made this back to being, in fact, let's do it this way. Let me write it as -1 over 1. Of course, wait a minute, it's negative. All students take calculus. We can see that sine is positive up here at the top, so I don't want those. I want to know when the sine is negative, and that's down here. Of course, so I could try and draw a triangle here, and that would make more sense because now the opposite is negative going down, and the hypotenuse is 1. But they're supposed to be the same length. The only time that can happen is actually if it's straight down. If this opposite moves closer and closer and then squishes right to the hypotenuse, that would be straight down when it would be -1 straight down, and the hypotenuse would still be 1. Even if it's straight down, the hypotenuse is never negative. So that's why it's actually at 270 degrees, or 3 pi over 2. Again, I actually think the knowing the graph of the sine function just makes it that much easier. So there's our answer, and it looks like that's our only answer for both parts, because they're exactly the same, and there's only one answer for this part. So there we have it.